So, anybody have any questions before I get started? Well, people showed up at least, so I guess that's a good sign. Or you're just bored. So we're going to be talking about extending the problem that we were discussing last week, which was failure. So we talked about how do you recover in a single node from failure. And failure in those instances are usually because the software crashes or the machine crashes or something goes wrong that's localized to that particular machine. They're trying to recover from errors. Can be really simple. You can just simply say, well, just start something over again. But as we begin to build persistence into what we're doing, so we're modifying multiple entries in a database, for example, now we have to do a little bit of work in order to make sure that when we restart, the system is back to a place where the software can work correctly. And I'm being a little hand-wavy here because the actual definition of what it means to be in a consistent state is domain-specific. If you're building the software, you're the one who gets to define what it means to be ready to start processing things again. Now let's move this problem, since, of course, that's an easy problem now. We'll define it as being easy. What happens when we start doing this across machines? When we have multiple different systems that are actually working with each other and need to remain in a consistent state? It turns out that even coordinating two systems and keeping them in a state where you can restore consistency on both of them is a harder problem than doing it on a single system. But we're going to use exactly the same technique. So last time I talked about building transactional journals, write-ahead logs. They're all the same basic concept, which is we record enough information that we can use that information to get us back to a consistent state. Well, when we expand this from one node to multiple nodes, what we're going to do is this is a very systems-y thing to do, we're going to add an extra level of indirection. Why do anything directly when you can do it through a table lookup? That's virtual memory in a nutshell, right? Except here, what we're going to do is we're going to build a recoverable log, a journal, whatever you want to call it. We're going to build that on top of these other systems. And we're going to coordinate between actually one of the terms that's used is coordinator, believe it or not. Monitor, coordinator. It's the same basic idea, which is now what we have is another agent whose job is to keep track of what different nodes are doing and and where we are in terms of doing something that crosses those boundaries. Because now we're talking about manipulating data in databases that are on different machines. Not the same database, but now different databases. And that's why you've got all those database readings, is that all of this distributed system stuff effectively came out of the database community when they started to say, gee, I'd like to have interactions between databases that aren't on the same machine. Now, one of the things that is typically different in this scenario is if the machine crashes and your database and everything you're working on is on that machine, it's all gone at the same time. But now we don't have that particular situation. Now what we have is a situation where one of the nodes has failed, the other one hasn't failed. Or maybe neither of them has failed and the network between them has failed. So we have a much more complex failure domain. Since our motivation here is how do we recover when things go wrong, you can see that the landscape is just a little bit harder than it was before. In the first design lab, This is exactly the problem we're trying to solve. That's why I pushed the design lab out, because I wanted to make sure that I had gone through this conversation before you started diving into the design lab and saying, okay, what's my solution to this particular problem? There are 3 different systems involved in the first design lab, and this is, of all of the recovery, honestly, all of the failure recovery systems we'll talk about, this is the one that you're most likely to implement. The really cool one is when we get to talk about Paxos and its variants. But the number of people who can actually successfully implement a Paxos system is vanishingly small, because it's really much harder, because we're going to go from 2 nodes to n. And it's solving a different problem than this one is. This one is solving a simpler problem. But of course, when we're done, we'll be able to combine these things. If you actually look at the DS labs, the lab we're not doing, which is the last lab, well, we're not doing the first 2 either, but those are the trivial, make sure, they're the Hello World projects, basically. The last one is, in fact, where you use both Paxos and you use a 2-phase commit protocol on top of Paxos. So we're going to be talking about the 2-phase commit protocol, which is how do we get what looks like 2 or more nodes to remain in consistent states after something goes wrong on any of those nodes across the network. So you're building a primary backup replication system. The primary and the backup need to apply an operation. One crashes, the other one doesn't. What was the outcome? What are you supposed to do? Remember, you want the system, and the system is defined as both of these, the primary and the backup. You want them to be consistent. The consistency model here is from the perspective of the client using the system. The system internally can be a mess. Externally, you want it to look absolutely pristine. You know, it's like when you clean your room and you shove everything in the closet. Nobody looks in the closet, they just notice it's all sparkling and shiny and it looks really good. That's what they're interested in. What you have to do is enough work so that when things go wrong, you can put it all back together. They don't need to see that internal mechanism. So in the distributed lock problem, which is essentially what the primary backup replication service is, what we need is a situation where different clients accessing our service won't notice if something goes wrong with them or with us. Now, the lock server example is interesting in that our service interface is pretty primitive. If I'm providing you a distributed lock service, you call, you get a lock on something, and then you die, I have no way of knowing that you're dead. And so we'll have to solve that problem. We'll build a dead detector. And people do that. They actually do build systems that say, I haven't heard from you in a while. Are you still alive? This is a wellness check. And after a while, they say, you must be dead. Now, this concept is really straightforward now, but in fact, when I was working with, I think it was Kerry Williamson, actually, who's at the University of Alberta now. He did this work on what he called leases. So the idea was that instead of just getting a lock, what you get is a lock that's like owning an apartment. It's good until the end of the lease. And at the end of the lease, you have either surrendered the apartment or we just assume that you're gone and we reuse it. Now, of course, in the actual apartment model, that might be a little uncomfortable, but hopefully it doesn't happen to any of you. So the basic idea was we have a way of detecting a failure condition. We've defined it that way. And that's a standard way of doing it now. The problem in the internal system falling apart is that if we have a primary and a backup for our lock manager, and the primary hands out a lock to client A but doesn't tell client the backup about it, and then it crashes, now the backup takes over. It says, I'm the new primary, and client B comes along and we give the lock to that as well. That's inconsistent. We have now made something that went wrong inside of our service visible to something outside of our service. Someone notices the dirty sock on the bed. You didn't do a very good job of cleaning this room, did you? So even though the individual primary and backup had logs, what they were missing was a way of coordinating their logs. Well, now I'm going to point out that, gee, we're back into looking at consistent cuts. We're in the distributed systems world because we don't actually know the order in which these things happened. We just need to be able to reason about them so that we can identify where we need to roll forward to or roll backwards to. We don't care which direction it is. All we care about is that the system can recover and remain consistent. So, high level, the client sees perfect behavior. They don't see this internal turmoil. They don't see this failure inside of the system because the system's guarantee is that it will provide a transparent service. This is what makes building distributed systems hard. I know there's at least one person in here who's taking 436C, which is cloud computing. The cloud computing people get to ignore this problem, mostly, because we can build services that guarantee this to them. Now, I said mostly because, well, it turns out that sometimes we allow them to get cheaper services by giving them sloppier results. That's a cost trade-off, not a correctness trade-off. All right, so our single node recovery pattern became failure, use the log, establish a recovery, either roll forward or roll backwards or some combination of them, and get back to what we know is a consistent state. Now, the interesting part about implementing these systems is you'll spend a lot of time verifying that your log gets you to a consistent state. It's not as easy as it sounds. Okay, it's easy if you've got one thing that you're keeping track of. Jesus is my distributed lock manager. I'm managing one lock. Not a lot of complexity there. But the moment this starts to involve a lot of different moving parts and a lot of different moving pieces, it becomes much more complicated. But that's what makes it fun. So conceptually, we don't care how you do that. Pragmatically, it's a lot of work. So this worked because we had one node with one log that generated our one source of truth. But with primary backup, whose log becomes authoritative? Who gets to be the boss here? Well, I know, we'll make the primary the boss. And that you can actually do that. But in fact, normally the way we end up separating this out is that we have a configuration. And we maintain that configuration independently of the primary and backup servers themselves. So when I want to know, I'm a client, and I say, hey, I want to talk to that service. How do I talk to that service? Somehow, there is some sort of advertising mechanism that allows us to discover the service. The advertising mechanism tells us where to send our request to. In the case of a primary backup, it's probably going to be send it to the primary. It doesn't have to be. There are designs where you can send it to the primary or the backup. They're just a lot more complicated. So we'll keep it simple at this point. So a client finds the service, says, this is the primary backup service I need to use. And it sends its request to the primary. The primary receives the request. But before the primary can apply that operation, it needs to make sure the backup also can apply that operation. Otherwise, you're going to end up in that split brain situation. So the primary and the backup must always agree on the state. And literally, when I think about designing these things, I say, what do I do if this fails? What do I do if this other thing fails? What do I do if this situation occurs? So in a case where I have, and this is exactly design project 1, which is DS Labs Project 3, I have a primary server, I have a backup server, and I have a configuration server, a view server they call it. And the view server is, in fact, nothing more than a versioned data structure. With three things, I have at least three different failures that I can identify right off the top of my head. Any one of those nodes could fail. Well, in fact, two of those nodes could fail, and that leads to some different analysis. If all three fail, you don't really have to worry too much. That's kind of like somebody nuked the data center and everything's gone. Fine. When you come up with a failure condition like that, and you say, I'm not solving this problem, document it. Be very clear in saying, this is not part of my contract. This is not something I can guarantee. That's perfectly acceptable. You will have to do that a lot. So if the primary and the backup always have to agree on the current state, then what do you do about ordering these things? How do you make sure that these things are applied in an order that is consistent? Now, in fact, in primary backup replication, you can do this fairly simply. How? I mean, I don't want to give it away, right? If you figured it out already, share it. If you don't know what it is yet, this is the point of Design Project 1. But I can tell you that it is very much about the order in which you implement the operations themselves. You can get more sophisticated. You can get tricky. I'm not saying that there aren't other solutions. What I'm saying is the simplest solution is, in fact, making sure that you apply things in the correct order here. And often that is, in fact, the right solution. Simplify by just insisting that the order must happen in a particular sequence. You're creating linearity. So, should the primary apply it and then forward it to the backup? Should the primary forward it first to the backup and then apply it? When does the primary send the response back to the client? Now, in our model, the clients wait indefinitely for the response. So we're keeping the model still fairly simple. Yes, it's complicated, but this is the simple, complicated model. The general solution to this is what we're going to call two-phase commit. And this was invented in the 1970s in the database community. Ultimately, credit is given to this guy named Jim Gray, who was actually quite brilliant and well known in the database community, and went on a day sail in outside San Francisco and never came back. He was leading the Microsoft research group in the Silicon Valley at the time. And it didn't last a lot longer. A couple of years, Microsoft had shut that down. So there's real people behind this stuff. There's real history. This wasn't always known. The observation was, if I can add another log to this, I can have what I call a coordinator. And the coordinator's job is, in essence, to keep track of what the state is agreed upon between the parties. And so literally what happens is a two-phase protocol. So in the first phase, we start an operation, a transaction. We then perform a series of steps within that operation, the transaction. And each of those nodes has its own separate journal, its own log. It's keeping track of what it needs to do in order to restore consistency if the transaction doesn't finish. The coordinator's job is just to keep track of the transaction. When all of the client's work is done, the client says, start a transaction, I need to change this database and that database and do these other things. And then it says, I'm done. Now what happens is that the coordinator will contact all of the participants in the transaction, which was at least 2 nodes, mean, there's no reason to do it if there's only one. But it could be more than two, and often in the real world, it actually is more than two. Think about when you do an Interact transaction, where the Interact transaction is between the merchant, their bank, your bank, and exchange, the Interact exchange itself, your account, their account. I mean, there's all these different things that are going on there. And those all have to happen together, all at once or not at all. So the coordinator just simply keeps track of what's going on, and then at the end it says, all right, now I'm going to check with everybody and see if they are prepared to commit. And it is literally in the protocol, it is begin transaction, operation, and then the client says, I'm done with the transaction. The coordinator says, we are now prepared to decide the outcome of this transaction. So it does what's called a prepare phase. It sends a message to all of the participants in the transaction and says, are you ready to proceed? Are you ready to proceed? Are you ready to proceed? If every one of the nodes that participated says, yes, I'm ready to proceed, then the coordinator makes the final decision. And it records that decision in its log. And then it sends a message out that says the transaction has been committed or the transaction has been aborted. What would cause a transaction to abort? This is literally a veto system. Two-phase commit is very simple in that it requires all the participants agree to commit the transaction. So in the prepare phase, when they vote for it, they all have to vote for it. Anyone voting against it means that the coordinator will come back and say, this transaction did not work. And it tells the client, it says, your transaction failed. It may not tell it why it failed, but it means the client knows that something went wrong and it will have to try again. How many times have you ever tried to use your credit card online or someplace and it doesn't work? There you go. We don't know what went wrong, we just know something did go wrong.
Sorry, so in this case, does the client talk to the coordinator or does it talk to...
He talks to the coordinator.
Okay.
Well, actually, you can do it either way, but ultimately the coordinator is the one that makes the decision on the final decision on whether the transaction committed or not.
Does all the nodes need to agree on the same thing? Or?
In two-phase commit, that all the nodes need to agree. Okay. All of the nodes and the coordinator all need to agree, and the coordinator casts the last vote. The coordinator will only vote to commit the transaction if all of the other nodes have agreed to commit the transaction. Yes?
What happens if one of the nodes crashes after saying yes?
It's an excellent question. It's where I was going to head anyway. So where can things fail? And that's exactly the right way to be thinking about this. It's like, what could possibly go wrong? Everybody's voted for this transaction, but before I heard what the outcome was, my process crashed. I come back 20 minutes later, and I'm like going, what did we decide? Who knows what we decided? The coordinator. So what you do is you actually go and ask the coordinator, what was the outcome of this transaction? Because you know it was pending. If the transaction aborts, each of the nodes that was part of that transaction will receive an abort message, and it has to roll backwards whatever it did in that transaction. So it restores consistency by saying, nothing happened. It was just your imagination. Pay no attention to the stuff in the closet. What do you do if the coordinator crashes?
You can add one more there.
And create another backup and then have a coordinator.
Yeah.
Oh, and it is really turtles all the way down here, isn't it? If the coordinator crashes, then in fact what will happen is, depending on whether or not it has written the commit record to its log. If it has not written the commit record to its log, the transaction is aborted. If it has written the commit record to its log, then the transaction will in fact is permanent, and it has in fact been adopted. But it might be a while before someone else can query and say, what was the outcome of that transaction? Was there a question? I saw a hand over here, I think. Yeah.
Can the participants talk to each other or only to the coordinator?
There's no restriction that they can only talk to each other, but in the simple model, we tend to do that because it eases the analysis. When you start allowing n-way communications, your state space is going to explode really fast, and the things that could possibly go wrong gets complex really quickly. But yes, you could have clients that are talking to each other, and that does happen in the real world quite a lot. But when we first start thinking about these problems, we tend to think of them from the service provider's perspective. And as far as we're concerned, what the clients are doing with each other is not visible to us. So we just assume that they're isolated. If they're not isolated, it's their problem to deal with the fact that they're not isolated. They've got another level of state on top of what we're providing. It's like, imagine you have coordinators of coordinators, which can happen. Wow, lots of questions now. This is great.
Does the coordinator only have logs then?
Does the coordinator only have logs? Conceptually, yes. When you implement it, though, there's nothing that says you can't put a coordinator on. You can be co-resident on a machine with one of the resources or one of the participants in the transaction. That's actually very common as a model, but it's not required. So conceptually, I think it's easier to just think of the coordinator as conceptually being separate, but could in fact be fate shared with one or more of the services. There's a question here and a question there. So I'll go.
So for each of the nodes, do they have their own local logs to keep track of which state?
If they have persistent state that they need to be able to undo, yes. If they keep everything in memory, then no, they actually don't.
So, like, building up on that, like, I had another question, but now I have another question.
You're just filled with questions today. It's awesome.
Yeah, but like you said that the nodes, the participants don't have to have a log of their own, but if they fail, how do they go back to the previous commit?
Oh, that's their problem. A log is a mechanism or technique for getting back to their previous commit. Mm-hmm. But if they don't have persistent state, let's say everything they have is in memory, they don't have any, if they don't have any, if everything is ephemeral, if they have no persistent state, they don't need a log because there's nothing for them to go back to. Sometimes, this is the weird part, sometimes what people actually build is they build monitors, things that are watching the transactions but not actually participating in them. So they'll register to say, yeah, call me back because I want to know what's going on, but imagine you're building a console, for example. You might build something that's just simply participating but doesn't have any persistent state. It's only got ephemeral state. So this is where I have to walk the line here carefully. The basic conceptual model is all of these things will have persistent state. But the reality is that as soon as people are like, ooh, cool, I could build something just to watch. There you go. Now you've got the voyeuristic service that just likes to watch things. And people do build that. It's very common to do that kind of monitoring. There was another question, I think. All right, well, if I missed you, throw something. Preferably not too hard. So the coordinator's log becomes the source of the truth for the decision about this transaction. Coordinator is a conceptual role. It could, in fact, be a series of coordinators that are used in different circumstances. You can build very complex models out of this, but the simple model is the one where we have a coordinator and it manages all of these things. And so we have our various service providers, and then we put another turtle on top of them. So it's just a stack of these things, and you literally end up building in distributed systems, you end up building layers of these. And you will see this happen over and over again, where we will take a basic technique and then we will build a more complex technique on top of that basic technique. So design project 1 is this primary backup, which is essentially what I'm talking about here today. The view server there is a very, very simple coordinator in that the view server is nothing more than a single configuration that says, here's the primary, here's the backup, and here's the view number. And that gets evolved based upon a set of agreements between the primary, the backup, and the view server. Not all, almost no real-world coordinator is nearly that simple, but it's nice to see something that's simple enough that you can sit down, reason about it, and realize, wow, this is actually harder to get right than I thought, and then say, now it's only going to get more difficult and more interesting, and this is why you get the big bucks for building distributed systems when we start trying to generalize this. Almost nothing in this field ends up being binary decisions. Almost everything ends up being a whole series of complex trade-offs. Simple often means lower performance. So when you decide that I really need to make this thing run faster, you end up changing things around so that it does run faster, but oh my golly, is it way more complicated. And as it gets more complicated, it's harder to demonstrate robustness. How many of you have built some piece of software that got a little out of control and way, way buggier than you wanted it to? I mean, it's a hazard in this field, right? It's like, oh, how hard could this be? And you start throwing it together, and then you start people try to put generality in. The curse of generality is it means all of a sudden the state space that you're exploring grows rapidly. The benefit of building a hello world is there's not a whole lot of generality there. You build something, and why do we do that kind of thing first? Well, because it makes sure we have our tool chain set up, not because it gives any deep understanding. Design Project 1 isn't quite that simple, but it's not intended to be much more complicated. And yet, I did say, it's often the most complicated solution you'll need for building even medium-sized distributed systems. The times we're going to need the more complicated stuff, which we'll spend a fair amount of time getting to, those are fun. But reasoning about them gets really hard. So, in two-phase commit, that's 2PC is the normal nomenclature for that. In two-phase commit, we have a coordinator that is responsible for starting the transaction, gathers up the votes from the participants, decides to commit or abort, and maintains some sort of persistent storage that records what the outcome was of that particular transaction. The participants are responsible for executing the transaction locally. Now, normally what happens is, you don't have to do it this way, but normally the conceptual model is the participant records all the things it's going to do in its log, and then when it gets the response that says this transaction has committed, it in turn commits those things, and it actually applies those changes. Now maybe it's holding locks on its own data structures, in which case then it applies those changes and releases that lock.
Don't we have the atomicity problem this big? It's like if there are multiple things to do, things to get wrong.
And what did I just do to get rid of that atomicity problem?
Log it, but then...
that was the first part of it, but the other part of it was you may have to wire locks or hold locks across it to make sure that no one else can change it at the same time. It is not the only way to do that. And in fact, transactional systems can get quite complicated because that's the simple model. And what did I say happens once you get the simple model built? You look at it, you go, the performance sucks. I'm going to actually try to tune this thing. And then you're going to go back and you're going to try and make it more complicated. So for example, you're going to try and build speculative execution systems, and you're going to try and build more complex locking. So the simple way to do this is the way that people start. Anybody ever built a hash map? A hash map data structure is very straightforward for this, right? The first thing you do on a hash map is you say, I'm going to put a reader-writer, or I'm going to put a lock on it. I'm going to put a mutex on it. And then you find out that, in fact, that mutex sucks because it means all of the reads on it are conflicting, even though they shouldn't be. So then you put a reader-writer lock on it. And then you find out that, of course, that's great, except it means that writes are really hard to get in there because the writes get starved. And so then you step back and you say, well, how about if what I do is I put finer grained locks, because I've got buckets, so I start putting locks on the buckets, and then you say, okay, great, now I've got better performance here. And then you get into the tricky part where you say, I'm going to do an operation holding a read lock that at the end, if I can do this operation, I'll try to grab the lock that I need as a write lock, uncontended, because you can't block, otherwise you'll create a deadlock situation. And if I miss, if I miss, then I have to undo everything and go back and grab the write lock. A very common trick that I have used in my own work is I look at a value, but I don't lock it from changing. So I'll have a read lock on it. I look at that value, and then later I'll look at that value and see if it's changed. And if it hasn't changed, let's see, it can't change, so what is it? So you do, it hasn't changed in a way that matters. That's the interesting thing. It's like reference counts. That's the case where I always ended up doing this. In a reference count situation, the only transition in reference counting that matters is the 1 to 0 transition. Because when the reference count drops to 0, normally what we do is we garbage collect it, we throw it away. But if I'm only holding a read lock on the 1 to 0 transition, this is the sleazy part, I notice that this is the 1 to 0 transition, so I drop my read lock, I acquire the write lock on it, I try to do the 1 to 0 transition again, and if that really does drop to 0, I garbage collect it. But maybe somebody else came in and erased in the meantime, and they bumped the reference count on it, and that actually can happen. So you can actually do unlocked increment and unlocked decrement except for the one case where it went to 0. It's kind of a mind game sort of thing. And you end up putting these kinds of optimizations in there. I probably went way over people's heads. Sorry about that. You end up putting these types of optimizations in there because they improve the performance of the system using atomic operations, compare and swap operations, these very specific mechanisms for doing atomic updates without holding locks. Locks are great, but locks end up suffering from performance bottlenecks because in almost any of the kinds of work that we do, we have hotspots. We will see that when we start talking about, so a key value store is really nothing more than a hash map. The beautiful thing about hash maps are that they are decomposable. You can actually take regions of the key space and divide it across different nodes. And so you then have a routing layer that says, oh, you're looking for that key, go over to that node and get it there. You're looking for that key, it's over there. And under the covers, we can actually move the keys around to do load balancing in a way that clients can't see. And we're going to do that kind of load balancing using, that's what the last DS Labs is actually, is exactly this kind of rebalancing. And we're going to use two-phase commit on top of replicated Paxos key value store. And then we're merging all of these things together. It's a lot of fun. But let's get back to something simple. This is the simple case. This is the two-phase commit case. This is the coordinator that has to make a decision. You come along, you can participate in this transaction without understanding the coordinator at all, just knowing a little bit about the protocol that you have to support and what to do if you crash and come back and you say, I've got this thing in my log, it said that I had voted for the to commit it, but I don't know what the decision was, so I have to go and I have to query the decision. What am I supposed to do here? Because I have to recover my state now, and to recover my state I have to go and I have to ask the coordinator, what was the outcome of this transaction? And the coordinator tells me. Just to walk through, I already walked through this once. This is the more detailed slides, of course, because you got to repeat things. The coordinator sends a prepare message to all the participants. Each participant makes sure that it has committed everything it needs to commit that transaction at that point. So for example, if you need persistent state, you are agreeing that persistent state, well, that state is persistent enough that it will survive even if you crash. So you will be able to roll that transaction forward. There are still failures that are outside of this model. This doesn't say, I put this stuff on the hard drive and then the hard drive failed, or the storage device, because nobody uses hard drives anymore, which is actually not true. But the storage device fails, and I can't actually roll that transaction forward. I have violated the transactional protocol, but I've done it in a failure domain that I didn't agree to protect against. I mean, everything can be protected against. How do you protect against the failure of a storage device? Well, just replicate the storage device. How do you guarantee against the failure of a storage controller? Because the storage device has to talk to a storage controller. You replicate the storage controllers. How do you protect yourself against power failures? Well, you put two power supplies in a physical rack. How do you protect yourself against the power itself going out? You put an uninterruptible power supply on each of your redundant power supplies. So you build redundancy into the system to make it more robust. But there are always failures further down that you don't protect against. And that's not what we're considering here. This is really trying to protect against the common class of failures. Now, what a common class of failure is will change over time as your system gets more complicated, as the demands on it become higher and higher. I mean, Amazon literally builds systems, as does Azure, as does Google Cloud, as does Oracle, as does IBM. They literally build systems that will continue to function correctly even if an entire data center is destroyed. Do you think any data centers have actually been destroyed? Oh yeah. Oh yeah, they've had entire data centers just destroyed. It happens. Failures really do happen. Hurricanes, earthquakes, tornadoes. There's one really interesting failure case that I used, which was in Australia. They didn't have enough people to turn the cooling in the data center back on. They had gotten rid of so many people that they physically didn't have enough people to flip the switches to turn the cooling back on, and the storage devices actually melted. Oh, that was pretty nasty. And these things happen all the time. You read them in the news, you'll even get to experience some of them. Every term I teach, there's at least one of these kinds of failures that bubbles up, and people actually notice that something stopped working. I think last term there was a big AWS outage that caused like a third of the internet to just stop working. And you too can build these kinds of systems. So once all of the participants have voted yes, we're ready to commit the transaction, then that's when the coordinator says, everybody else is ready, I've now recorded this transaction is officially committed. If anyone says no, and no doesn't necessarily mean they actively said no, it could also be a timeout. We could say, if you don't say yes within a finite period of time, we will interpret that as a no, and we will abort the transaction. If and only if all the votes are yes, then the coordinator writes a commit to its log, and it sends a commit message back to the participants. The participants then commit locally, they release any resources they're holding, locks, and they acknowledge that to their coordinator. If anyone votes no or there's a timeout, then the coordinator aborts the transaction in the log and sends an abort to all the participants. The participants roll back, and the participants acknowledge it to the coordinator. So there's a lot of communications that's going back and forth here, but the point is, it gives us a system that ensures all of these different nodes will all either apply this, modulo the failures that we've explicitly excluded, or none of them apply it. This is also similar to the Designing Data-Intensive Applications book, which you probably have. And this is one of these famous MIT lectures on distributed systems. So this is very common. This is something that's been taught for at least 40 years now. Probably closer to 50. Because the two-phase commit protocol was designed in the early to mid-1970s. So, like I said, the coordinator's log is really the last vote. Before that last vote, we don't really know the outcome. It is literally a binary condition now. Despite the fact that we have all of these different participants, the actual outcome is ultimately decided by one of the participants, the coordinator. The decision becomes final. This is important. And I was talking about this before last time, is once you've committed something, you don't want it to roll backwards. There are these principles in database design and in distributed systems where it's called durability. And the idea of durability is we won't see the past come back. We won't roll backwards once we've said something has happened. And can be propagated to any participant that asks. The point is that if you participated in the transaction, you might have crashed in between. You need to know what the actual outcome was. So there's a way for the participant to ask what was the outcome of that transaction. A client can also can ask that because a client is also a participant in that transaction. And it can ask the coordinator, hey, what happened? This is persistent information because it's in the coordinator's log. So, this is really just taking our single node solution and strapping it to a bunch of other nodes participating. But in the end, our single node solution works here because it's making the controlling decisions. Even though the work it's doing is actually to coordinate with these other nodes. So if a participant crashes before we've finished voting on the transaction, let's see. So this is a participant. This is a participant's perspective. If the participant crashes before, then the coordinator times out the participant. After voting yes, but before receiving the decision, the participant crashes and comes back and says, I voted. It asks the coordinator, what was the outcome of that transaction? And the coordinator says it was committed or it was aborted. And then the participant applies that decision. Now, this point is, assuming this participant actually had persistent state, it uses its own log to restore consistency. Roll forward, roll backwards. Straightforward. If the coordinator crashes, if that happens before it's written its decision, then the participants are waiting, and they're holding locks, right? They have resources. They're blocking other people from making forward progress. A new coordinator reads the log, sees that no decision was recorded, and it says, I'm going to abort this. In theory, you could build a recoverable coordinator. There's nothing that prevents you from doing that, but the simplest model is to say, if the coordinator crashes and the new instance of the coordinator comes up and it reads the log and it says, this was indeterminate, I'm going to say, the transaction aborted. Otherwise, you'd need to have some sort of recovery protocol to build on top of that to say, hi, this transaction was in the middle of being prepared. Can you tell me if you'd actually voted yet or not? So you have to go and regather the votes. That's a lot harder. Once the decision has been made, if the coordinator reads the log and the decision is in the log, the new instance of the coordinator knows that the old one approved it. Decision's made, done. Propagates that decision to all the participants. If a participant already heard the decision, it doesn't matter because it didn't change what it's heard. So sending the same message twice shouldn't actually change the outcome here. We're not changing history. That's the key point here. The decision is durable once the coordinator's log has been committed. So what do you have to put in that coordinator's log? This is the failure first model. I failed. What do I need to know in order to recover? So the recovery says, let's see. So I begin a transaction. I need to know who's involved. Now, you could declare that up front. You can actually build it dynamically as you go along. There are different ways and models of doing this. Let's keep it simple. We have two participants. The first participant is asked to vote, and it says yes. The second participant is asked to vote. It says yes. Then the decision is made by the coordinator who says, we commit. That's the critical entry there. Step 4. Step 4 is how we know what the outcome of the transaction is. Once that has actually been committed to storage, we consider this transaction to be done. And then we send an acknowledgement to the nodes, P1 and P2. You don't actually have to send that acknowledgement, by the way. And in fact, one of the things I commented before is that when we build these kinds of protocols, it's usually safest to build it out explicitly, step by step by step. So you can reason about why those steps lead you to a recoverable system. But then you look at that and you go, well, you know, what I could do is I could piggyback the ACK of this transaction onto the start of the next transaction. One fewer message. That's the optimization phase. But when you go through and you iteratively improve and optimize this protocol down to a point where you've reduced the number of messages by 50%, and that's not uncommon, then you try to explain it to somebody, they're going to be going, huh? Why are you doing that? Because you went through the steps. You saw the basic protocol. You understood why it worked. And then you saw how you could optimize it. But when you try to explain the optimized protocol to somebody, there's magic now because they don't understand why you're doing that. And that trick of getting rid of the begin and the ACKs, begin, ACKs, ends, those are all the kinds of optimizations that we routinely apply. So it's not uncommon. I think it was the first time I built this, is that, I used to put an explicit begin record in there, and then you were like, well, why would I do that? I'll just have a bit. So the first thing I put in my log says this is a new transaction. Easy. I've reduced an entire message into a bit in the next message. Perfect, absolutely wonderful. If I'm sending an ACK to both of these and an end, I don't know why I would do that. I would just simply send one of them. And then I'm going to say, oh, gee, I start a new transaction. I'll just simply piggyback the previous transaction. I'll say that transaction was committed. And I'll make that one message instead of two. And then we keep whittling it down, and we realize that over time we can make this very efficient and do the same thing, but it's much harder to explain. That's why I'm taking it in this approach. I'm saying this is the failure, here are all the steps, but you're going to collapse these steps in an actual implementation. So, in the primary backup with the view server as the coordinator, the client sends a put, because these are key value stores, because everything is a key value store, a hash map. The primary logs it. It says, I'm going to do a put of the value 5 into the variable x, and then it sends that to the backup server. And the backup server then logs it and says, I'm going to put x, set x to 5, and it puts it in its log, and then it sends an ACK back to the primary. Now the primary crashes. What happens? We don't actually have a coordinator here for the key value store. We just have two systems. The key question here is going to be, did the client get a response? And if the client didn't get a response, then it doesn't matter what we do. Either returning the old value or the new value will be correct. If the backup does have the data, in other words, it put a prepare in there, but it hadn't actually committed that yet, then the question becomes, what should that new primary do? Because the backup has just turned into the primary. Now, in fact, as long as the client didn't receive the old answer, the backup can send either the old answer or the new answer, and it's correct. Because either of those would have been potential outcomes. But this is a put operation, not a get. So I should be careful here. It's the two-client case that becomes complicated here, not the one-client case. So one client does a put, and he doesn't get an answer back. The client's going to send the put again, because this is at most once. So the server guarantees at most once, the client guarantees at least once. The client keeps sending the request until it gets a response. And the intersection of at least once and at most once is exactly once. That's why we build this model, because this makes it easy for us to reason about things. And then when we want to get fancy about it and say, well, you know, maybe we want something much more complicated than that, you can reason about that. But get the fundamentals here, the simple model down. That foundation will work then. So this is actually the kind of thing that you will be considering in Design Project 1. So after a primary crashes, what happens in Design Project 1 is that the view server detects the failure, typically some sort of a heartbeat. You haven't heard from the primary in a while, and the view server doesn't declare that the primary is dead, but the view server will in fact allow the backup to ask to change the configuration to make it the primary. That's the protocol. Did you have a question? Okay, you had your pen up earlier. I wasn't sure. Because you were looking down with the pen up, and I was like, maybe not. Now, this is playing fast and loose with terminology, because in fact, if you read the design project, what it says, it's not the view server that changes the view. The view server accepts proposals to change the view, and then accepts the primary authorizing a change of the view. Now, the interesting case there is when the proposal is from the backup to become the primary. And the time you do that is when the primary hasn't been heard from for a while. The primary is timed out for whatever reason. What is the difference between a primary timing out because it crashed and a primary timing out because it's not connected to the network? That's a question you'll have to actually answer for Design Project 1, and it sounds like you're going to have to think about it a little bit. Yep.
It could just be that when it crashed, all of its memory disappeared, not the storage, and then when it lost data, the thing that was in the memory still in the
How does someone other than the primary know that it's crashed versus fallen off the network? In other words, if I'm the backup server or I'm the view server, how do I distinguish crashed versus a temporarily off the network? Exactly. And that is the important point to observe, is that you can't, but the primary, so how does the primary know when it comes back, the network gets restored, it reboots, it doesn't matter. How does the primary know that it's no longer the primary? Someone tells it. Who? What? What in this system? There's only three things here. The primary falls off the network, comes back on the network, or the primary reboots and comes back. What actually tells the rest of the world what the primary is? Sorry?
The coordinator got.
In this case, it's the view server, right? So the view server is in essence a configuration service. That's all it is. It's just this basic configuration data. And each time you change the configuration, you bump a counter in it. We're back to a Lamport clock. Since we have a Lamport clock, we have something that is monotonically increasing, so we can tell if this state is newer than the state that we previously saw. Now, since it's monotonically increasing, it's never going to go down. And so now we have a way of reasoning about what we're seeing. So the primary goes down, comes back up, queries the view server and says, what's the current view? The view comes back, and its number is higher than the view that the primary saw, and it says, I lost. I'm not the primary anymore. The transitions here are what matters around the views. So when the system first comes up, the view server says there's no primary. So the first server to actually talk to the view server says, oh, there's no primary. I'll be the primary. And it proposes a view change. It says, the view number is 1. I will propose view number 2, and puts me as the primary. Now, if someone else races at the same time and also proposes as a primary, only one of them is going to win because the view server is going to choose the one that it received first. Probably. I mean, I suppose you could randomize it, but the logical thing to do, and the simplest, is just to choose the first one you hear from. And so now that becomes view number 1. Well, that other proposal to change the view to view number 1 is rejected because view number 1 has already been created. So now we have a way of breaking that tie between 2 or more servers that each offer to become the primary. Once the primary has taken control, now we can serve as clients. The client sends a put request or a get request, and the primary can respond to the put or the get. Another node says, well, okay, you didn't take me for primary, so how about if you take me for secondary, for backup? And it asks for a view change that says, make me the backup. Well, now it becomes more interesting because the primary has to agree to the view change. Why? This is probably one of the most important things in that design project, and you need to think about that. What does that new server's database look like? What should it look like? That's a different question. You have a question?
Not a question. It should look like the latest one, like the primaries.
Yeah, since this is a replicated service, it would be kind of nice if the backups database looked like the primaries. So you literally cannot allow the backup to be registered in the view until you've guaranteed its database is identical to the primary's database. That's the reason the primary has to approve the view change. Once the backup is in sync with the primary, the view change can now be promoted. That does mean that if there is a failure when the primary is the only thing that exists and the primary fails, the system's dead. So you do have this vulnerability there. So the view server detects a failure and tries to promote the primary should be driving this, not the view server. But the backup should actually say, I want to be the primary. Or the primary should actually say, the backup is dead, please remove it, because I'm no longer keeping it in sync. Why would I do that? Why would I wait until the backup comes back? It's another one of those things you'll have to think about in this design project. So, in general, the simplest way to do this is going to be to apply changes to the backup before you apply them to the primary. And the reason for this is, so the client sends a request to the primary. The primary applies the operation. This is the naive approach. The primary applies the operation and then responds to the client and then forwards it to the backup. Now what we have is a problem that if the failure occurs after we've sent the response to the client, but before the backup has applied it, the next time a get comes in on that value, it will get the wrong data. That's violating our contract. That's making our messy closet visible to the rest of the world. That's not what we want them to see. We want them to see something that is absolutely perfect. And perfection in this case means we don't answer the client until we know that the primary and the backup both have that data. Since the client is doing at least once, if it doesn't hear from the primary, it will retry. At some point, it will go and check the configuration server. It'll go to the view server and say, oh, the view has changed. I'm sending the request to the wrong server. And then it will send the request to the correct server. If you send from the primary takes the request from the client and sends it to the backup first, and the primary then crashes, and the backup is promoted to primary, the client will eventually figure that out, send the put request, and the backup server will say, I've already processed that request, and it will say, okay. And we will end up with a consistent behavior. That's how we hide this moment of insecurity. We carefully order the operations so that the system will do something that is correct. If the backup hasn't recorded that and the primary fails, the backup gets promoted, the client's request to put that value will come in again, because remember it's doing at least once, and the backup that's now the primary will process the request, and the behavior will work correctly. And you literally end up, when you're building these kinds of systems, thinking through exactly these kinds of sequences. What happens if it goes wrong here? What happens if it goes wrong here? What happens if it goes wrong here? And then you implement this thing and you start testing it and you find out there's some failure case you didn't consider, and you go back to the drawing board and you say, okay, how am I going to handle that one? And over a period of months and years, you build up a much better appreciation for, wow, things can fail in ways I never imagined. Your imagination will grow. So this is that correct order. Client sends a request to the primary forwards to the backup applies it, acknowledges it to the primary applies the operation, and then responds to the client. That will give you a recoverable sequence. This is, in essence, a walkthrough of Design Project 1, which opens at the end of class today. So the goal in Design Project 1 is for you to try and build a robust design. I provided some examples. If you really want to, you can copy those, but instead, my suggestion would be look at them and then implement your own. Because the learning isn't in seeing or copying someone else's design here. The learning is in actually sitting there and saying, what would I do? And you don't have to do it the way they did. And you don't even have to do it the way I just described. I described what is probably the simplest path through that. But maybe you're one of those people who goes, you know, I'd like to make it complicated. Maybe you do that with your relationships too. No judgment there. And you say, I think I'm going to want the primary and the backup to be able to respond to clients, because that'll make things a lot more fun. That's a much more interesting scenario now, isn't it? And you can think about, what would I build that system to do then? And of course, the goal of making it complicated is then someone else is going to try and implement it. And they're going to try and figure out if the design that you wrote is really as trashy as you probably will think it is when you finish it. And the benefit of sharing the good examples with you is you can see what good examples look like. I mean, I don't know how many of you have written designs before. Not a lot, right? And yet this is what you will do in distributed systems all the time. Next week we'll actually have a guest lecture. He will be talking about formal modeling tools, a technique that was literally developed by this guy named Leslie Lamport. I'm sure you've never heard that name before. That provides a formal mechanism for describing models of distributed systems so that we can verify them. So just to summarize, 2PC is a layered recovery model. You can stack these things. People do it. You can actually build a coordinator on coordinators that are sitting on top of services. You could build coordinators on coordinators on coordinators because, of course, if, it's like a cake. One layer of a cake is okay, 2 must be better, and if you can put 6 of them, oh yeah, baby. Very thin slices. Oh, so much sugar. Perfect. As I always say that ironically because, of course, we all know that the more layers you put in a system, the slower things get and the more complicated they could potentially get. But sometimes that is the reality of what you end up building. When you build things on top of these beautiful distributed system services that we build, they end up having to suffer through all of this kind of layering of different systems and properties. And it's not uncommon to have 5 or 6 layers of functionality, each of which is dependent on other layers, all of which resides on this piece that one poor person in Nebraska has been working on as his pet project for the last 30 years. There's an XKCD that literally shows the modern internet, and there's this one little piece at the bottom that holds it all up. That's actually the network time protocol, I think, is the one that he was referring to in that cartoon. And there's several of these things. There's the DNS protocol and the network time protocol and these very basic services that people built years ago that we rely on. All right, so next time we're going to talk about the weakness in two-phase commit, which is we have a coordinator. What do we do when the coordinator hangs? And how do I distinguish a hung coordinator versus a not on the network coordinator? I can't. So I'm going to make things more complicated because I'm going to solve this problem. And this is pretty much the way the rest of the term is going to go. We are going to fix one problem and create another one that will be even more complicated. Blah, blah, blah. Nothing interesting there. Yep. The self-assessment should have gotten shorter now. Instead of having the punishing 13 questions, I think it samples 2 out of the pool. If you have questions, we've got lots of TAs now. They've got office hours scattered throughout the week. I kept moving mine around because I was trying to avoid theirs, so there would be somebody available each day. So I think I'm on Wednesdays now at like 1:30 or something. All right, see you on Thursday when we can talk about 3-phase commit. Nah, you don't need beyond 3. Then we get into Paxos. Don't worry, Paxos will just melt your brain.